Hello, my name is Robin Grappin, and I am going to introduce you to the publication named Regularized Infill Criteria for Multi-Objective Bayesian Optimization with Application to Aircraft Design. This work, part of Agile 4.0 project, has also been done with the participation of Nathalie Bartoli, Youssef Douane, Joseph Morlier, Paul Save, Thierry Lefebvre, and Jasper Boussenmaker. This teasing video will handle with the following subjects. First, I will introduce the black box problems to show the importance of metamodels. Then, I will present the necessity of treating problems with more than one objective to obtain Pareto-optimal solutions. Finally, I will talk about our contribution to the state-of-the-art through our regularization method for infill criterions and its application to an aircraft design problem. There are several choices to make in order to design an aircraft. It can be the shape of the wings, their size, or the position of the tail. All of these parameters are design variables in a design space. The engineer will have to choose the best combination of design variables in order to have the best aircraft. This question of optimization implies a comparison function, measuring the efficiency of a specific design. Points of interest can, for example, be the weight or the aerodynamics of the obtained structure. A generic optimization method aims to find the minimum of such an objective function corresponding to an optimal design. Unfortunately, these objective functions are very expensive to evaluate, as they may ask to make an entire finite element modelization to get their value. Thus, it is impossible to use classical optimization methods such as gradient descent or evolutionary algorithms, which ask for a lot of evaluations of the objective function. We have to define a limited budget of evaluations of our true problem. With a few design points and their associated objective value, we must build a metamodel of the function to minimize. These points represent our current knowledge of the problem. This modelization is made using Gaussian process. The obtained surface is our first estimate of the objective space. The metamodel so generated is in fact a distribution of probability. At each design space point is associated a mean and a variance in function of the uncertainty we have about the true objective value at this location. It is visible in this figure that the points used to build this model are more sure than the one far from them. If we go back to the true objective function, we may regret how far the model is from the reality. To improve the knowledge of our function, we may have to wisely select new points, and that is what is called Bayesian optimization. But before we enter in the details of this process, let us ask ourselves, what if we have a second objective? Going back to the physical problem of designing an aircraft, we could have the wish to have a light structure, but also a small drag coefficient. With the same reflection as before, we can get some prior points of measure in order to build different metamodels. This distribution of probabilities will be considered as independent here. Each of these objectives may have different locations for their minimum, leading to a conflict. Compromises must be found. In mathematics, a point which is not beaten by any other design point on both objectives is called a Pareto optimal point. Their set is then the Pareto optimal set drawn in orange in these figures. We can mention that the minimum of each objective is necessarily included in this set, as no design point can be better than them on this objective. If we look at the values of these design points on the objectives, we can plot the Pareto optimum front. An engineer can then decide to not choose point having more than minus zero point 0.6 on the first objective, as they increase a lot its value without an interesting gain on the second one. The advantage of the metamodels is that we can run the usual multi-objective optimization methods for cheap on them, such as generic algorithms. Unfortunately, with so few points, we are still far from the real Pareto optimal set, and the Pareto front obtained is far from the real one. The true values of the Pareto set according to the multi-objective function are also not the same than those according to the models. Then, Bayesian optimization becomes a key point, using our knowledge to choose a next point to evaluate in order to better know the objectives, especially in the areas of interest. An infill criterion is a function of the distributions of probabilities giving better values to points with high potential. Its maximum is then the best point to compute. Iteratively, the models become closer and closer of the reality. The Pareto front in these plots is computed on the meta-model, so it can take values better than the real ones, but the evaluation of the associated design points will of course not. Across iterations, the models become closer and closer from the reality in the areas with performant designs. Once the budget of evaluations of the physical model is done, we have a sufficient amount of points at interesting locations to run a genetic algorithm on the accurate metamodel's means. The obtained Pareto front is then close to the exact one, and if we compare the true values of the objectives at the estimated Pareto set, the accuracy of the metamodels is now evident. The key point in this method is the way to choose the next point to evaluate. This is done using an acquisition function, also called infill criterion, which is a function giving to each design space point a score depending on the value of the model's mean and variance at this location. The best point to add in order to improve the metamodel is then the maximizer of this acquisition function. Common choices in the current multi-objective Bayesian optimization methods are the probability of improvement and the expected hypervolume improvement. When we are dealing with difficult problems or high-dimensional design spaces, it is not rare that these acquisition functions don't give good points. The main issue is that we have to balance between exploration of a design space to not only propose points from a local minimum and exploitation to modelize well the areas of interest. It also happens with these functions that their maximizers aren't found because they are flat or have local minima. To counter this phenomena, we created a regularization technique that we called YB2S, taking an acquisition function and modifying its output. The obtained function is the new acquisition function, which is smoother, avoiding to fall into local maxima or to have flat regions, but also has a better balance between exploration and exploitation thanks to the regularization. After implementing this, we applied it to a concrete aeronautical problem with 5 design variables. This is the obtained Pareto front, and each point of the obtained Pareto front is associated to a design point of the Pareto set. Some optimal designs are plotted on this scheme. To obtain these designs optimized both in terms of fuel mass and operating right empty, we only evaluated our true problem 115 times, what took around 5 hours. In terms of comparison, applying NSGA2 directly to the true problem necessitated 85 hours of computation for the 2,500 calls.